it gives you a lot of information. Normal contains a lot of information about the surface. Okay. But the key thing that is giving us the information about the surface is not the normal, it's how the normal changes the direction. Now the question is how you can compute this change in the normal, what you need to do, or how we can do it. So the obvious way to do it is to differentiate it. And the notion of differentiation that we have developed is covariant derivative. Okay. So what we want to do next is to define an operator in the terms of the covariant derivative of the normal vector. Okay. And we're going to study. Okay. So let's get to the, make yourself comfortable with these basic things, especially pictorial things. Actually, calculations are not difficult; they are easy actually. But the real thing is that we must be able to think about all these things correctly. So here's the thing. So what we want to now have a covariant formulation of covariant derivative formulation of curvature. This is what we want. Let's begin with the definition. So let's take X be any vector field on M in R3. So let's take a manifold for surface in R3. Okay. And let be the normal vector. Normal vector, and you can treat N as the Gauss map. Okay, you can treat N as the Gauss map. Normal vector are the Gauss map. Okay. Then let me define an operator L. Okay, I'm going to specify its domain and what? Codomain. After which the domain is pretty clear because it's taking the vector, and the vectors are here basically by vectors are being tangent vectors. So obviously the domain of L is what? It's the tangent bundle. So X is an element of tangent bundle. Okay. And the output that it gives the covariant derivative of the normal vector in the direction of N. Okay. Just like let's compute the normal vector or the changes in the normal vector in the direction of vector X. Okay.
क्लासिकल इसको देख सकते हैं.
क्यों नहीं देख सकते? What would be N prime? So for N prime, where does N prime lies?
N prime N के perpendicular है.
N के perpendicular. Okay. N के perpendicular. How does the things that is perpendicular to N look like on a surface? So what must be? It's not precisely tangential, but it's something tangential. So I'm saying is that take a vector field, take a particular direction on a surface, okay, and move the normal vector in that direction. And that's what we were doing all the time. So move sometimes normal vector in this manner and see what's going to happen. Okay. This minus is out of convenience. It's just a convention.
We are treating N as vector field subfield also.
I am at the moment, I can treat N as a vector field, or a vector, or you can I mean, if you want to get a bit more sophisticated, you can treat n as the Gauss map actually. Okay. So that if you do the computation at a point, then yes, n of p is a vector and x is also a vector at that point. Okay, but abstractly, yes, this is. Why you have a minus here? This is out of just convenience actually. Okay, because it reduces the number of minuses afterwards. Okay. So if there is an expression with 3 minuses and 1 plus, okay, it will turn it into the 3 pluses and 1 minus actually. So it will reduce number of minuses afterwards. It's just out of convenience. So it's not something much interesting. Are you getting the point? So what does this map is meaning? That map is taking a particular direction, and we are kind of pushing to move the normal in that particular direction. And then what we want to see, let's see what happens actually. Let's see what happens. So studying this operator gives you lots and lots of operators. This operator has a name. L is called, so there are different names. It's sometimes called shape operator. Okay. Sometimes called shape operator. But some people are using, for example, the book here is also called the, this, what we call Weingarten map. Weingarten map. Okay. Weingarten. And G-A-R-T. Yes, Weingarten map. And before starting investigations about this operator, so obviously we're going to see that L is linear. Why it's linear? Because the covariant derivative is linear. So obviously L is also linear. So it's a linear map. So if it is a linear map, and we are talking about finite dimensional spaces, because X is, M is something in R3. So, you are from R3 to R3 or R2 to R3, okay? So something finite dimensional. So we know that L is going to have some matrix. And that matrix would be very important. Anyways, so here's the definition. Before getting into it, let me define something that I'm going to use later. It's called the Lie bracket. By the way, I gave you a problem on Lie bracket on one of the exam actually, which simply says that if you have two vector fields x and y, then the Lie bracket of x and y is the commutator of x and y actually. Okay? And what do I mean by commutator is defined to be the vector field xy minus yx. The difference of xy and yx. Okay? Where x and y are x comma y are vector fields. Okay? One exercise for you to do is that prove that the Lie bracket is by the way, this would be a map from where to where? Lie bracket, I can treat this as a map from tangent bundle cross tangent bundle into tangent bundle actually. Okay. Is a linear derivation. So this map is a linear derivation. Okay. In other words, it's linear and follows the product rule of differentiation. So that's what you have to prove it for yourself. It's also a proposition here, and if you wish you can see it from here, but you can give it a try yourself. So once you have this definition of the commutator, the Lie bracket, now we are in position to specify basically what is or what must be the codomain for the operator Li. In other words, what is the domain and the codomain of the operator L? So this Weingarten map or the shape operator L is a map from tangent bundle to the tangent bundle, okay, and specifically I can also say that this map, if you specify a point, if you take a tangent space onto the M, is going to throw where? Throw where? So here's the thing. N is throwing the points to the N of P. So N of P is a point, okay, on sphere actually. Okay? So what can I treat, what will be the meaning of computing the derivative of N of P actually in the context of sphere actually. So what you can see that when Weingarten map is doing nothing, is just, so it's like taking the point P here, drawing a tangent space here, and taking the point here, drawing the tangent space here. Then Weingarten map is a map that takes the tangent vectors from here and throw it onto this tangent space. But we can actually prove that this tangent is space on the sphere is same as this tangent space. So it's pretty isomorphic actually. Okay. Why? Because both have the same dimension. And any two vector spaces of same dimensions are isomorphic to each other. Okay. Alright. So I can treat in this manner L as a map from TPM specifically to the TPML. Alright. And this is linear transportation. Okay. So this statement is a bit imprecise, but this is more precise. So L is a kind of a map that takes a tangent vector at a point and throws it onto another tangent vector at a point. Okay? And it's a linear transformation.
So that point won't be P.
I'm sorry?
This is tangent bundle on P, right?
Oh, okay. So this would be obviously tangent space at N of P, but this is isomorphic to TP actually. So therefore I'm saying that you can safely replace it with the TPM. Anyway, so it's a linear transformation. So I'm not going to prove linearity. Linearity L inherits, so prove it for yourself. Linearity from the connection. Okay, from the connection. The only thing that I would like to prove is that it indeed takes a tangent vector from here and throws it onto a tangent vector. Okay, so this is what that I would like to, I am interested in showing it. We want to show that if L sends x to the Lx, then this Lx is indeed part of the tangent bundle on this. This is what that is about. How can I do it? So in order to do it, I'm going to begin with an observation. So what is n? For n I know, for the normal vector n I know that the inner product of n with itself is itself is,
Derivate both sides.
and if you compute, so if the inner product of n with n is 1, because this is equal to the magnitude of n square, and I know that the unit, so n is a normal vector, so its magnitude must be 1, so this must be 1. So in other words, if I compute any kind of derivative of this guy, then it must be 0.
Zero.
Okay? So let us compute the covariant derivative of this inner product on both sides. And let's see what we get. So let's take the covariant derivative of n and n, so I know in advance that this is 0. Okay? I can assume safely that this connection is compatible with the metric. Okay? So it's compatible with the metric. You remember the compatibility of a connection with the metric? That says that if you take the connection and operate onto the inner product, then kind of product rule is satisfied. Okay, so what does this mean? That del x of n plus okay, n of n. So this must be true. Is it making sense? But what is del x of n? So I can say that this is same as minus lx n. Okay, and okay, so this must be also n minus lx. But since you don't have a complicated kind of an inner product here, it's just what do you call it's what?
Dot product.
It's a dot product, so it's commutative also. So I can treat this as minus 2 times of inner product of lx x, and that's equal to 0. In other words, lx x is 0. So what does this show? So x is a tangent vector. So it's a part of the tangent bundle, and it is something. So it has a dot product. Okay, lx.
N, sir.
I'm sorry. Yes, it must be n. Yes, it must be n. So lx has an inner product. It must be n then as well here. Okay. So this map has a dot product n with 0. So what does this mean? So it must be a tangent vector itself. This implies this guy must be the tangent vector format. Okay. So what does this shows? That this map is indeed what? A linear map from tangent bundle to the tangent bundle. Now let's investigate some of interesting properties of. By the way, did you thought about yesterday's question that I posed, that how the determinant of a matrix that I give you with
Zero.
differentials and the first and the second fundamental form coefficients, equating it to 0 gives you the two directions. So, did you reach to any conclusion? You haven't got time to look at it. Here's the thing. So I think I have something like du dv and dv square, something like this, and efg and efg. So on a point, these are numbers. So if you solve it, okay, and equate it to 0, what you will see or you will get as an answer by solving this determinant, you can get an answer as u equal to c and v equal to some constant, okay, c1, and v equal to also some constant c2 actually. Just think about it. Because if all these are numbers, so what you only remain with the expression in the terms of u's and v's, which can be manipulated and somehow solved to get something u equal to c1 and v equal to c1. So if you fix your u, so u is representing any direction basically on the surface. So when you say that along, from any direction, this direction is the principal direction. Okay, and this is another principal direction in which the normal curvature is going to be maximum or what do you say, minimum. Okay, so these are pretty complicated stuff. But now we're going to see actually that if you know such kind of a map, in other words this Weingarten map actually, or Weingarten map or the shape operator, the principal directions, because this is going to be a matrix actually, everything is finite dimensional, so you can find a matrix, and it's in fact going to be a 2 by 2 matrix actually. Okay, so the eigenvectors, we're going to prove a result. The eigenvectors of this matrix are the principal directions, and the eigenvalues of the matrix, this matrix L, the matrix representation of L is the the principal curvature set. So the principal curvatures and principal directions are hidden in this what do you call it, map L. So combining all these things together.